introduction, and thank you so much for that introduction. I'm so pleased to speak with you all today about exoplanet frontiers, the search for habitable and inhabited worlds. And how I'm going to do this is first, I'm going to review why we're doing this. What would a habitable and inhabited planet look like in broad strokes? Where are we in terms of exoplanet science in characterizing exoplanet atmospheres? And then what would it take to look for planets that are like Earth or could maintain global biospheres that could be remotely detectable? And so one big question in astrobiology is what is the prevalence of life in the universe? Because astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. And of course, most of the universe is outside of our solar system. We know many things about our universe, the nature of galaxies, much physics up to mere fractions of a second after the Big Bang, but we know almost nothing about the distribution of life in the universe. This is a civilizational goal, and one that we are so privileged to live in a time where we could start to make progress on this. So we're aided in this goal with the observation that Earth itself, our planet, the only known habitable planet so far, is a dynamic, geologically active and living planet the evidence of life on our planet is manifest in its remotely detectable spectrum. And so I'm showing two key things here. On the left, what I'm showing is what's called an Earthshine spectrum of our planet. And so this is light from the Earth that's reflected off of the moon and then reobserved by ground-based observatories on the Earth. And it's split up into its component wavelength or colors. And these dips and lines correspond to the presence of different molecules in the atmosphere or different features on the surface. And so I will get more into this later in the talk, but some things to point out are oxygen that comes from plants, ozone from the chemical processing of that oxygen, carbon dioxide from volcanoes and geologic processes, and methane from various forms of biology. On the right is a graph that shows the fluxes or production rate of different gases produced and processed by life. And note the logarithmic nature of the y-axis. On the left is the Earth as it is today, and you see large amounts of oxygen, nitrous oxide, which is laughing gas, methane, things like dimethyl sulfide, all made by microbial or multicellular life on Earth. And then on the right part of the chart is an example counterfactual non-living Earth. And you can see that these are very different from each other. And so in principle, we could look at the distribution of gases in an atmosphere and fingerprint which one corresponds to a global biosphere and which one is not inhabited. We can extend those Earth biosignatures possibly to other Earths. And that means that the gases that don't necessarily accumulate to large concentrations on our planet perhaps could accumulate to large and detectable concentrations on an exoplanet. And on the left, I've listed just some examples of the gases that this could include, ones we may be familiar with: oxygen, ozone, methane, made by photosynthetic and methanogenic life, respectively, nitrous oxide, which is a product of nitrogen metabolism and present in Earth's spectrum, and also more exotic gases that are made by life on Earth but don't accumulate in our atmosphere to significant concentrations like methyl chloride or dimethyl sulfide. There are also surface features like the so-called vegetation red edge. This is the strong contrast, apologies, between the chlorophyll visible absorption and visible light and strong reflectivity in the near infrared that's present in photosynthetic organisms. This is used to map vegetation on Earth today, and in principle, if globally distributed, could be a biosignature on exoplanets. And finally, there could be temporal changes in both of these things or non-biosignature gases that are nonetheless processed by biology, such as carbon dioxide. On Earth, we have seasonal growth and decay of vegetation, which leads to rises and falls in CO2. And that, in principle, could be linked to biology. All of this, of course, doesn't consider the spectral signatures and detectability of those gases and features, which will depend on their abundance. However, we're getting a little bit ahead of ourselves. Um, First, we have to understand what planets are out there, how common are they, are there enough Earth-like planets to characterize, and where are we in terms of the science of looking at the spectral signatures of atmospheres like our planet. What I'm showing right here on the left is a diagram that's showing the number of this planet discoveries by year linked to the detection type. So there are numerous ways to find and characterize exoplanets. Two big ones are the so-called transit method and the radial velocity method. And briefly, the transit method is a way of detecting planets by inferring their presence indirectly by the dip in the brightness of the star as the planet transits or eclipses the star. So you can think of it like a miniature eclipse where the strength of that eclipse is dependent on the size ratio of the planet to the star. And if this repeats at regular intervals, we can infer that's due to the orbital period of the planet, and we can detect the planet that way. Another indirect way of finding planets is through the so-called radial velocity method. And the principle behind this is that for a large enough planet, the planet doesn't just orbit the star orbits the planet's star center of mass, and the star is in fact being gravitationally influenced by the planet. If the star is heading towards us in part of its little orbit around the center of mass, it will be blue shifted and shift its spectral lines in such a way that ground-based observatories can infer that shift, and then it'll redshift as it goes away from us. And if this repeats in a periodic way, that corresponds to the orbital period of the planet, then we can infer the planet indirectly. And you may ask, well, why can't we just take a picture of the planet and find it that way? And there are, in fact, some planetary systems that are found through direct imaging. However, this is an immense challenge for many planets. The reason being that if we take our Earth as an example, Earth is outshone by the star, by our sun, by a factor of about 10 billion at visible wavelengths, or 10 to the 10. What we can do from the ground today is we can take pictures of very hot, far away planets, orbiting stars at distances that are much further than, for example, Jupiter is from our sun, which is 5 astronomical units. In this case, both the planet is sufficiently separated, and because the planets are hot and young, they're bright in near infrared wavelengths, and we're able to see them. We are getting better and better at the technologies that are able to do this. One piece of technology that's really crucial is something called a coronagraph, which nulls out the light and reveals the presence of the planets. So I will get to this as applied to Earth-like planets later in the talk when I talk about the future Habitable Worlds Observatory. Another common method of finding planets is something called microlensing. And the idea here is that if you have a foreground star passing briefly in front of a background star, you can get a temporary increase in brightness due to gravitational lensing. The gravitational warping of the foreground star causes a magnification effect, which is observable on the ground, although it's a chance statistical occurrence. And if there happens to be a planet orbiting that foreground star, then you can get a secondary dip that will reveal the presence of that planet. You can never go back to that system, but if you look at regions of the sky that are highly populated with stars, what you can do is build a statistical understanding of how common planets are. And that's really critical. Many of our observatories for transit, as I mentioned in the previous slide, have been made by the Kepler mission, which was looking at a region of the sky between in the summer triangle in the night sky for many years, and then transitioned to a secondary mission where it looked at different regions of the sky. And the Transiting Exoplanet Survey Telescope, which has been mapping the entire sky, but is only sensitive to planets with orbital periods less than about 60 days or so. So this bounty of exoplanets has given us a good statistical understanding of some exoplanet properties. What I will emphasize for this audience is that most known exoplanets are not habitable. They are not like Earth. There are detection biases that favor detecting large in radius planets and massive planets. Of course, the planets that are large in radius are easier to see with transit method because the ratio of their size to the size of the star generates larger transit dips. And more massive planets because those generate more gravitational influence on their stars, which can be viewed with Doppler spectroscopy or that Doppler shift method that I mentioned. What you can see here is a plot that shows as a function of orbital period, and this is a log plot. So this would be 365-day Earth orbital period would be right here. Earth is marked here. And then the planet mass in terms of the mass of Jupiter. And so you can see Jupiter right here. And so this is the distribution of planets. And so some of this is statistically robust, and some of it is a result of detection biases. For example, the fact that we have few planets near Earth in orbital period and mass is not reflective of a deficit of those types of planets, but simply the fact that those planets are very hard to detect. On the other hand, we see an abundance of planets that are in between the size of Earth and Jupiter that have very close in orbital periods. And that is a real result. There are planets that are very close to their stars and very massive. We call those hot Jupiters. As I'll describe, those end up being very good targets for atmospheric characterization. So our studies of exoplanets have revealed different planet types. And so this is a summary in terms of the sizes of the exoplanets. The sizes reflect the compositions in many ways. So in order to get the size of Jupiter or larger, planets have to be primarily composed of hydrogen and helium, light elements. And so we see many gas giants that are the size of Saturn or Jupiter. We also see Neptune-like planets, so planets that are similar in size to Neptune and Uranus. We see many terrestrial planets. These are Earth-sized or smaller. They're made of rocks like silicates, like our Earth. Some could possess oceans and atmospheres that show signs of habitability and life. We also have super-Earths that are more massive than Earth, lighter than Neptune, and are primarily rocky in composition. Some of these may or may not have atmospheres, depending on how close they orbit their stars and their atmospheric evolution. It turns out that planets that are intermediate between the size of the Earth and the size of Neptune are actually very common. We know that they are, in fact, the most common types of planets in the universe. And while this green bar is lower than this orange bar, we know for a fact that it's easier to find larger planets than it is to find smaller planets. And so when we correct for those statistics, these intermediate planets, these super Earths and mini Neptunes, end up being the most common type of planet. We don't have any example in our solar system, which is very intriguing. And those planets come in two flavors. And so what I'm showing here is a plot that shows, as a function of planet size, the number of planets we have that have an orbital period of less than 100 days. And we have two peaks. One peak that's represents planets that are larger than Earth, we think are primarily rocky in composition, that have no hydrogen or little hydrogen envelopes, and more puffy planets that are smaller than Neptune, but larger than super Earths, that we think have substantial hydrogen atmospheres. And there is a radius gap between them, which we think may reflect atmospheric evolution. For example, some of these planets that have gaseous envelopes may over time lose them and become these smaller rocky planets without hydrogen envelopes. So in addition to characterizing these worlds by size, we can also characterize them in terms of their temperature or insolation. And so what this plot is showing is different planet classes. So we have stellar flux relative to the amount of light that Earth receives from the sun, and planet radius. And these lines correspond to different boundaries where there are different condensing species. So if you get close enough to the star, the planet's atmosphere actually is composed of very refractory elements like rocks. Rocks become vapor at high enough temperatures. And so you can even get silicate atmospheres. You can get things like zinc sulfide clouds and really hot planets. You can go further away and you can have steam atmospheres that are very hot. So any water is no longer stable on the surface. It would be in the atmosphere and presumably could escape through time. Although we have atmospheres that are so massive that they can hold on to their hydrogen. So gas giants called hot Jupiters. We can get to the point where water is a condensing species, and this would correspond to the habitable zone for our planet Earth. And then if we get further away, even CO2, which in our atmosphere is a key greenhouse gas that prevents the Earth from becoming frozen, that itself will freeze and depose on the surface. And so you can no longer have a habitable planet. It's too cold. And then we can see some analogs to our solar system like cold Neptunes and cool Jovians like Jupiter and Saturn. So we're quite interested in the planets that are rocky, that lie within the zone where water could be liquid on the surface. And we are also intrigued by the possibility that some worlds that are large enough to have thin hydrogen envelopes could, in fact, have habitable deep global oceans that could potentially maintain habitable conditions, although we don't know that for sure. You may have often seen this concept in the terms of the habitable zone. The habitable zone is a conceptual region around a star where it is not so hot that the ocean, any putative ocean, would boil away from the planet, and not too far away where it would freeze. There are many assumptions built into this habitable zone. I have no time to get into it in very big detail, but it assumes that there are some negative feedbacks that are happening on a planetary scale, like the carbonate silicate cycle feedback on Earth that maintains CO2 over geologic timescales and prevents our planet either from freezing for long periods of time or getting so hot that the oceans boil away. What you can see here is a plot that shows different as a function of a flux received by the planet and a function of the temperature of the star they're orbiting, where the boundaries of the conservative and then optimistic habitable zone lie, and then some known planets filled in. And what you can see is that there are many more known planets in the habitable zone around M-dwarf planets. These are dimmer, redder, cooler stars than the sun and more numerous. And that's reflective of the detection biases I mentioned before. It's easier to find these planets around smaller stars because the contrast ratio between the size of the planet and the size of the star is larger, and also because they have shorter orbital periods. This is another plot that's showing the relative abundance of these different stars, more stars that are cooler, redder, dimmer than the sun. And there's some intermediate between these cool red stars and our sun called K-dwarfs. As the star gets brighter, the habitable zone moves out and also has a more area. Okay, so we'd love to characterize these potentially habitable planets, but first we have to look at the planets that are actually easier to characterize. And so far, the easiest planets to characterize have been the hot Jupiter planets. Okay, so these are planets that are comparable to the size of our Jupiter, but they orbit very close to their star, much closer than Mercury does to our sun. These are, of course, artist conceptions of several hot Jupiter planets. How exactly do we do this? One tool we can use is called transit spectroscopy. The idea is that as we're looking at the planet transit across the star, some light will filter through the atmosphere. Some of that light will be allowed to pass through, and some of that light will be blocked by the molecules that are present in that atmosphere. One key parameter in understanding this is the scale height. So the scale height talks about basically the vertical extent of the atmosphere. And it's positively related to the temperature. So the hotter the planet, the more scale height there is, the bigger the signature you get from the atmosphere. And it's negatively correlated to the mean molecular weight of the atmosphere. So hydrogen atmospheres that are light are easier to see than heavier atmospheres like N2 atmospheres. And the surface gravity. So planets with higher surface gravity have lower scale heights, and have higher scale heights, and with higher surface gravities have lower scale heights. This is all very important, and I'll continue remind you about the scale height issue. Now, how do we identify the molecules present in these atmospheres? Well, every molecule has a unique spectral signature. That is, it interacts with light, infrared, visible light uniquely. In the near and mid infrared, these are due to vibro-rotational transitions that cause different rotating and vibrating modes in the molecule. And these are akin to the electronic transitions that you may see in an atom, where you can go between energy layers, but you can't. You can go between energy layers, but you can't have an energy layer that's between one or the other. And so there are certain transitions that are allowed, and there are certain transitions that are not allowed. This is very similar. The vibrotational states of these molecules are quantized, but there are billions and billions and billions of lines. When they bunch up, you can get absorption bands, and these absorption features are unique to each molecule. So when we look at a transit, we can look at the size of the planet effectively as a function of wavelength. And the size of the planet as a function of wavelength is a window into what molecules are present in the atmosphere. And that's easier to see, of course, where you have larger scale heights, which means our large Jupiter planets with hydrogen atmospheres that are hot are easier to look at. Our biggest tool in the last few years for characterizing exoplanet atmospheres has been the James Webb Space Telescope. It's a 6.5 meter telescope versus 2.4 meters for Hubble, so it's much bigger. It's actively cooled to very low temperatures, and that's key for looking in the infrared. And to illustrate exactly how powerful JWST has been, I'm showing here some plots. And if you look at this, these are model hot Jupiter atmospheres, and then the black points are actual data from the Hubble Space Telescope, which can look in the visible and very near infrared, and the Spitzer Space Telescope. And what you can see is that for most of the spectrum in the near infrared, we have no data. And take a look at the size of the data points here. The error bars are quite large. And so this was the situation before JWST. We had large regions of the spectra of planets where we could not access, and those areas where we could access, we had large uncertainties. Once JWST launched in late 2021, we gained unprecedented ability to characterize planetary atmospheres. And of course, we started, due to the scale height issue, with planets that had that were very massive, that had large scale heights. And so we favor those hot Jupiter planets. And so this is an example of a transit of about 0.5 Jupiter mass planet called WASP 96b. This is one of the first exoplanets that JWST looked at. It detected water in the atmosphere to high confidence at these wavelengths, many of which the Hubble Space Telescope does not have access to, and in only 6.4 hours of observation, which is an incredible feat. And so this was one of the first detections of molecules by JWST. JWST soon after made the first detection of carbon dioxide in a hot planet atmosphere. And this is in another region of the near infrared, where at about 4.3 microns, where CO2 has a large absorption feature. And you can see this data is very, very good. We have detected this molecule with very high confidence. Not only that, there are smaller molecules, less abundant molecules that JWST is able to characterize. And so folks making this detection notice that there is this kind of feature right here at about 4 microns. And a lot of effort was put into understanding where that feature came from. And it turns out to be from sulfur dioxide. And this sulfur dioxide is not from volcanoes, because this is a hot Jupiter planet. There are no volcanoes. It is in fact a result of photochemistry. And so this is also the first evidence of photochemistry directly detected on an exoplanet. And briefly, the way that this works is that light from WASP 39b can split apart water and hydrogen sulfide that are present in abundance in this Jupiter atmosphere. that sulfide and that oxygen can then combine together through a series of photochemical reactions. This was predicted by models before it was observed, and form sulfur dioxide. And the evidence of that sulfur dioxide is present in the spectrum. And this was a team effort by many, many people, one of whom was an author of the photochemistry paper, Shangming Tsai, who's now at ASIA, but was briefly at UC Riverside. So, putting all this together, how do we use these tools to look potentially habitable planets? One idea, and you'll hear this later in the series, so I won't spend a lot of time on this, is maybe looking at planets that could be habitable but are in fact larger than the Earth and have hydrogen atmospheres. And again, this is due to the scale height effect. We have lighter hydrogen, which would make hydrogen-rich atmospheres more amenable to atmospheric characterization in transit. Um, and so the idea is that some of these planets that are in between the size of Earth and Neptune could have deep water oceans and a thin hydrogen atmosphere that overlies that. And if the conditions are right, that surface ocean potentially could be habitable. They call these Hycean worlds or hydrogen ocean worlds. And again, the fascinating part about this is that we actually have the capability today to characterize their atmospheres and look potentially for signatures of habitability and maybe life. And so there was recently a paper a year and a half ago or so about finding carbon molecules in one of these atmospheres of one of these potential Hycean planets called K2-18b. And what was really great about this study by Madhusudan et al. Is that they detected with high confidence two carbon-bearing molecules, methane and carbon dioxide. And these had not been seen together before in a planet of this size. And so this is a really, really important study for that reason, unprecedented data. There's a lot of controversy over does this planet maintain habitable conditions? And a tentative claim of a detection of a very interesting molecule called dimethyl sulfide, which on Earth at least is made predominantly by marine algae and other forms of life. I won't talk too much more about this other than to say that observations are ongoing, and you will likely hear much more about this from the author of this study later in the series. If we want to do this for Earth, in principle, this is possible. What I'm showing here is a transmission spectra of the Earth. That black line is a reconstructed transmission spectrum from LIM soundings. This is an orbiting satellite that's looking through the limb of Earth's atmosphere, and then reconstructing a spectrum, a transit spectrum of the Earth as if it were seen from interstellar distances. And then a radiative transfer model and retrieval model is used to fill in the absorption features. Okay, so the planet is bigger at wavelengths where different molecules are absorbing. And you see here many interesting molecules from this perspective of detecting life. Those include ozone, which is a product of a photochemical byproduct of oxygen, which is made by photosynthetic life on Earth. You see evidence of methane on Earth. Methane is predominantly from methanogenic microbes. N2O, or laughing gas, which is also a product of nitrogen metabolism made by microbes. And you even see evidence of our technosphere through chlorofluorocarbons present in the mid-infrared. Now, this is sort of cheating because this is perfect data without any noise. And we know that looking at Earth-sized planets around distant stars is going to be very noisy and very time intensive. And there are not very many targets that are amenable for observations with JWST. And that is what the next slide is illustrating. And so what this is showing here, there are limited truly Earth-like planets accessible with JWST. So one, our star is a G star. There are fewer of those intrinsically. As we go to later spectral types, or if we go to smaller stars, the number of stars increases. The stars that are amenable to observations in transit are the coolest, smallest, reddest stars. And that's just because the size of the planet relative to the size of the star is more favorable. Also, the planetary system, the star has to have a transiting planet. And most systems, we're just not geometrically aligned for that. So what this plot is showing is known exoplanets as a function of installation and atmospheric transmission signal. And then the gray bar shows the set of installations or the amount of energy that the planet is receiving that's consistent with habitability. That is, the oceans could exist. They wouldn't be so hot that they would be boiled away, and it wouldn't necessarily be so cold that they would freeze. And there's one system that's clearly preferable, and that is the TRAPPIST-1 system. And the TRAPPIST-1 system is a set of rocky planets, um, 7 rocky planets that orbit a very cool, dim red dwarf star 41 light years away called TRAPPIST-1. The system is very compact. It could fit entirely within the orbit of Mercury around our sun. But because the star is so cool, the habitable zone is also very close. And hypothetically, numerous planets within the TRAPPIST-1 system lie within that habitable zone, including maybe D, certainly E, F, and maybe G. So the TRAPPIST-1 planets are our soonest opportunity to probe temperate rocky exoplanets with transmission spectroscopy. Um, One big question is, do many of them have atmospheres? And this is because we know that although these stars are common and they're amenable for observation, these cool red dwarf stars are also very active. They produce a lot of X-ray emission that could strip away atmospheres over time. So even if they had atmospheres, are they habitable or not? That's up in the air. And even if they're habitable, do they have life? So and if so, is that life detectable? Are there atmospheric biosignatures that are accumulating? There are so many unknowns, and so we'd really be lucky to find life in this system. We only have one of them, one really good target. Nonetheless, we should look. What we do know is that the evidence suggests, at least at the present time, that the innermost planets, TRAPPIST B and C, may not have atmospheres. So far, JWST has made a couple observations of B and C using a technique called secondary eclipse spectroscopy. And this is looking at the star plus planet light, and then the light from the star when the planet goes behind the star to infer and extrapolate the light from the planet in the mid-infrared. And what this is showing here are the two data points collected by this 2023 study, and then how much flux we'd expect if the planet had a CO2-rich atmosphere. And in fact, the measurements are consistent with no atmosphere at all. So the measured temperature that we have of TRAPPIST-1b is consistent with bare rock. In other words, that there is no atmosphere, um, and if there is an atmosphere, it's very thin. So we don't know. There are some, again, uncertainties on that measurement, but so far, evidence is consistent with TRAPPIST-1b at least not having an atmosphere. There is a study that I'll mention only briefly because it's complicated that looks at the coupled evolution of planetary atmospheres in the TRAPPIST-1 system and asks the question, given the fact that B and C don't appear to have atmospheres, what does that mean for D, E, and F? And it turns out not much. E and F, for example, could have atmospheres even though B does not have an atmosphere. And in fact, this study here predicts a 50% chance that B doesn't have an atmosphere from information we knew of before we had those transit observations. So in the most ideal circumstance, we would find an Earth around TRAPPIST-1. If we did, it would look something like this. There are many, many, many studies by many, many different groups imagining what if one of the TRAPPIST-1 planets had a habitable and inhabited atmosphere. And this is just one example by Meadows et al. 2023. And what you can see here is that if such an atmosphere existed, there would be spectral features from carbon dioxide, CO2, oxygen would be difficult, if not impossible, to find, water, and maybe ozone. In principle, this spectrum could reveal the presence of a global biosphere, it would take many, many, many years to collect. And unlike the previous spectrum I showed you, it's not cheating, it's showing simulated data and simulated noise. So if we're very lucky, this target could tell us that Earth-like planets, if there are Earth-like, truly Earth-like planets in the TRAPPIST-1 system, that they are present. And there are a very limited number of targets that are alternative to TRAPPIST-1. Looking for the future, and I'm almost done with this talk, I want to talk briefly about the Habitable Worlds Observatory. The Habitable Worlds Observatory is the next flagship mission that would supersede JWST, that would come after JWST. And it was recommended by the American National Academy of Sciences Astronomy and Astrophysics Decadal Report for the 2020s. And it recommends a large aperture, ultraviolet optical near-infrared telescope that would enable transformative astrophysics. And it would be the first telescope designed specifically to search for signs of life on planets outside our solar system. And so while JWST has the capability, potentially, to find life around a limited number of targets, this telescope would be specifically designed to study a robust number of samples, survey 100 habitable zones for signs of habitability and life on orbiting planets. So this is a simulated high contrast image of the solar system as if it were a distant stellar system. You can see a coronagraph is nulling out the light from the star and revealing the much fainter light of the planets. And you can see Earth. Earth is blue due to the Rayleigh scattering in our atmosphere, which you look up, you can see the sky is blue. And then you can take this light and split it into its component wavelengths. And if you did that, and not cheating with simulated noise, you'd get a spectrum like this, where the blue line is the actual truth, the actual input spectrum. The yellow points are simulated data points, and the gray lines are their simulated uncertainties. If we, and then look at the y-axis, this is in terms of flux ratio, and here's this 10 to the negative 10 value I told you about. So if we were able to get this kind of data, we're not just looking at the outer part of the atmosphere, we're looking down into the atmosphere and potentially, if we have cloud-free paths, all the way to the surface. This type of spectrum could reveal the presence of an atmosphere through Rayleigh scattering. That's this blue slope here. It could reveal the presence of water vapor, which would not prove the existence of an ocean, but be consistent with one, through several absorption bands of water. We could infer potentially the presence of photosynthetic life through oxygen absorption features and ozone absorption features. This ultraviolet feature here is evidence of our ozone layer. We could also see potentially evidence for carbon dioxide, which shows the planet is volcanically active, and could give us an idea of the greenhouse warming potential of the atmosphere. And so if, you know, and we could even, if we had maybe more methane than exists on Earth today, see the evidence of a methanogenic biosphere in addition to our oxygenic one. In looking at the capabilities of LUVAR and the promise of LUVAR, or sorry, the promise of HWO, LUVAR is a precursor study of the Habitable Worlds Observatory. We're not just thinking about the Earth as it exists today, but we're leveraging our geochemical archive of Earth history and the evolution of our atmosphere to think about how would we look at Earth or exoplanets that look similar to Earth at different periods of Earth history. And so if we go back in time just a mere 600 million years, we have a planet that has some oxygen, but much lower amounts of oxygen, maybe low enough not to see. But we could infer the presence of that oxygen indirectly through ozone. And we may have stronger signatures of CO2 and methane. If we go even further back in time, about 2.5, 2.6 billion years, we have an even different planet. In the Archean eon, there was no free oxygen in the atmosphere, but there may have been extensive amounts of methane and even a hydrocarbon haze that made Earth look more akin to Titan than it does to our planet today. What would be amazing about the transformative nature of the Habitable Worlds Observatory is that not only would we get habitable planet candidates. But by designing a telescope capable of detecting habitable planets, we would reveal a whole myriad of other types of planets. It would be easier to detect larger planets and characterize them. And so we would get rocky planets outside the habitable zone. We would get sub-Neptune planets. If any of them are habitable, they would have even larger, stronger signatures. We would be able to study exo-Neptunes and exo-Jupiters in unprecedented detail. This spectrum here shows an example of that, where each panel is a different hypothetical planet, similar in some ways to a planet in our solar system. And then the simulated error bars are the white gray crosses here. And what you could see is that for exovenuses, exojupiters, and exoneptunes, we could detect with high fidelity their absorption features and infer the composition of their planet. And that would give us insight not just into habitable planets, but habitable planetary architectures. Are we more likely to find habitable planets with Jupiters, without Jupiters? These kinds of questions could be answered by HWO. Just a couple more slides left. I am part of the Living Worlds Working Group for HWO, which is tasked with building this driving science case for the telescope. How do we detect life? What are the different types of biosignatures we can look for? What are the other things that we have to keep in mind? How can we rule out abiotic false positives or geologic and atmospheric processes that could produce gases that we would misattribute to life, but are in fact abiotic? And so we're thinking about all of these things. The timeline for this is most optimistically somewhere around 2040 and maybe in the 2040s decade. That's consistent with JWST. In its timeline, it was recommended in the 2000 Astronomy and Astrophysics Decadal Survey and launched in 2021. This was recommended in the Decadal Survey that came out in 2021. So 2039 or beyond would be very consistent with the timeline from JWST. And I'll end the talk with this quote, which I think is truly great. This is from the National Academy of Sciences Decadal Survey. If planets like Earth are rare, our own world becomes even more precious. If we do discover the signature of life in another planetary system, it will change our place in the universe in a way not seen since the days of Copernicus. And so we are really at the precipice of understanding whether global biospheres like Earth are common or rare in the universe. And within 20 years or so, we could have a solid, statistically robust answer to that question. And with that, I'll end and take questions. Thank you.